Welcome, everyone. We're thrilled to be with you again. This is GREMax Quantitative Reasoning with our focus on data analysis and statistics. We're really excited. It's a super fun lesson, and we're going to dive into, as always, some real GRE questions, but also build on the foundations of the drills and the skills that we will then apply. As always, please, we'd love to hear from you. Introduce yourselves in the chat, ask questions, really engage. This time is for you. Our goal is to invest in you and be of service to you in your grad school dreams. So with that in mind, here we go. We're gonna briefly reintroduce ourselves because we always have new folks chiming in. So for those of you who have been with us, bear with us for just a few minutes as we go through our introductions. But as always, I'm Jonathan Herzog. I'm the head of GRE content here at Testtaker. And I love GREmax. I love Testtaker, and I love the GRE in particular. By way of background, I completed my JD at Harvard Law School, MBA at NYU Stern, and undergrad at Harvard College, and have been teaching and tutoring and teaching classes in the GRE for over 5 years now. And one of the principles of GREmax and Testtaker in our hiring is we only hire folks who were not naturals at the test. So what that means is we had to suffer through and reverse engineer down to first principles without having the best resources at our disposal. And so that's what we've worked on to create, is to really deliver 10x the quality, 10x the value for you in less time and with fewer resources. So that's really what we're thrilled to share with you today, and joined by my colleague, Daniella.
Hi, everyone. I'm Daniella. Thank you so much, Jonathan, for that introduction. I did my undergraduate at UC Berkeley, followed by my master's at Cambridge, where I completed an MPhil in public policy. And then I have been studying for the GRE and applied to JD PhD programs. And I've been accepted to top 10 PhD and JD programs using the GRE. And I think it's a really powerful tool. My background really was struggling with the LSAT. And I thought the GRE was a really good option. So I look forward to encouraging that pathway, especially for those who haven't agreed with the LSAT in that way.
Absolutely. And for those of you looking, again, for a more comprehensive or general overview, definitely feel free to go to the Testtaker YouTube channel. We've done a series of webinars at this point on the GRE as a whole and the opportunities available to you with the test, as well as verbal and quant analytical writing. And we're excited to dive into a portion of quant today. All right, so again, just as a brief reminder, for those who haven't joined us before, the way we think about quantitative reasoning on the GRE is there's this myth that it's basically a math test, and it's not. Rather, it's a reasoning test. The GRE is a reasoning test that uses the language, logic, and syntax of high school and middle school mathematics and the English language. So keep that in mind as a frame for our deep dive today. All right, and these are extremely common refrains that we even shared ourselves when we were preparing, including, I'm just overthinking, I'm just running out of time on quant, I'm not a math person, I'm not a geometry person, or relevant to today, I'm not a stats person. These are all euphemisms for we haven't yet mastered the quantitative reasoning skills sufficient for our target score. I believe there was a question that might have come in. Oh, great. We have a link directly to our previous webinars. Thank you so much. All right. Substantively, the areas that we cover in quantitative reasoning for the GRE are arithmetic, algebra, geometry, and data analysis. Today, we have the great fun and fortune of diving, if our pen works with us, into data analysis. So here we go. Let's hear that. Data analysis. All right, so we're going to start out with a little comic strip, which may or may not resonate with you, depending on your background. But I used to think correlation implied causation. Then I took a stats class. Now I don't. Sounds like the class helped. Well, maybe. Now, for those of you rolling on the floor laughing at this hilarious comic, fantastic. For those of you maybe not on board, we'll dive into that today and in our logical flaws analysis that we did last week in analytical writing of conflating correlation with causation. Another fun quote to start us off, to orient ourselves to the world of data analysis and stats, is this famous quote, often misattributed to many folks, but it goes, "There are three kinds of lies: lies, damn lies, and statistics." And indeed, we like to ground the reasoning work we do for the GRE in our real lives, in tangible current events, to understand why this even matters. Because sometimes when we're going through the motions of questions, we're like, why am I studying exponents again? Why am I doing these stats problems? Well, this is extremely pertinent, especially if you want to work in research or in public policy or any role of leadership after pursuing your graduate education. So data and statistics are riddled all over the news, all over headlines, and having literacy and dexterity, understanding statistical thinking is an essential skill for not buying into the BS and being able to decipher and interpret information and truth for yourself. I see there might be another question in the chat. Apologies as I just quickly checked that. Yes, XKCD is making a comeback. All right, so we've seen this time and time again in debates and in heated online controversies around vaccine efficacy and interpretation of what does it mean when we compare a placebo group to a vaccinated group. And we find that in a particular sample, there's a 66% less risk estimated efficacy, or an 85% less risk of severe cases for a particular vaccine. It's really helpful and vital to have our own foundations, bottom-up drills, to build that skill and build that mental muscle of interpreting and deciding for ourselves fact from fiction. And again, those lies, damn lies, and statistics. So here we go. Statistics. We're used to colloquially referring to average this, average that. But there are actually a number of ways of expressing the average. The most common is known as the mean. The mean, strictly speaking, has an exact definition. It is the sum of the terms divided by the number of terms. So mean, or the average, is equal to the sum over the number of terms. I like to write it as X bar. You can write it as AVG for average. You can write it whatever notation is familiar and comfortable for you, but it's going to be super helpful and unlock a lot of value and impact going through quant questions if we literally write out this definition for ourselves as we go. Average is equal to sum over number. We see this fancy notation here. Again, just another way of presenting it. This is just a summation side that says, hey, you're going to add from term I equals 1, the first term, to I equals n, the nth term, which could be 5, 10, 126, all over n, again, the number. But again, if you don't like that summation term, don't worry about it. Just write sum over number. All right, so just as on the verbal portion, or when we're doing logical reasoning questions, key terms, key signifiers of formal logic, we want to literally transform them in our mind to what they mean in an if-then statement. So too, when I see average or the arithmetic mean, or we're going to look at a number of other examples, I think sum over number, sum over number, sum over number. Okay, a couple of important corollaries and different types of measurements of average, of the center of a data set. Corollary number one is, and this is just our arithmetic in cross multiplying, is that if the average is equal to the sum over the number, then as you see there, I like to use X bar, but if you wanted to use AVG, average times the number of terms is equal to the sum. So we're just cross multiplying there. But the GRE likes to package things in fun, different ways, different wrapping paper. So it's on you to see and to interpret them accordingly. So corollary one, average times the number of terms is equal to the sum. They can also call this lots of different things. They can call it and hide the arithmetic mean in per capita language. They can use the wrapping paper of, well, if equally split. So just key signifiers we're going to get used to interpreting, hey, I see arithmetic mean, sum over number. And I can then configure this in any arrangement by cross multiplying. Similarly, corollary number two, we'll see an example of this in practice today. You can combine averages, right? So if we know average one is equal to sum one over the number one, right? The number of terms in that particular data set, just a collection of numbers, which we tend to notate as such in braces or brackets. And let's say we have average two is equal to sum two over number two. Again, for data set number two, which we just notate as a collection of numbers in braces, then we can combine the sums or the numbers or the averages in different ways to unlock different missing pieces. So again, breaking down the arithmetic mean to its components can be super valuable on test day. All right, we've got the arithmetic mean, the sum over the number of terms. What about the median? The median is just the middle number of a sorted set of numbers. So a couple of key terms here. The middle number of a sorted set of numbers. But they got to be sorted in ascending or increasing order, right? So if we have 1, 2, 3, that is increasing ascending order. But if we have 2, 1, 3, which data sets can be presented in lots of different ways on the GRE, lots of different wrapping paper, you're going to have to do the work to reorder the data set in ascending order if you want to find very easily what the median is, which would, in that case, be just the middle number. So, corollary number one, the median is going to just be the middle value for an ascending set of an odd number of terms. We just saw this. Our data set is 1, 2, and 3. And as we go, I'm just going to be picking really simple numbers today to illustrate some of the concepts. And this is a useful skill to apply yourself in practice and even sometimes on test day, is picking easy, simple numbers that satisfy a set of rules. So just the middle number there. Corollary number two, the median is the mean, the arithmetic mean, of the middle two values for an ascending set with an even number of terms. So it may not actually be a listed value. So let's say we had 1, 2, 3, and 4. All right, so what this is telling us is the median is going to be the mean of the two middle numbers. So we can just know it or intuit it, or we can calculate it. It's going to be 2.5. But again, that's because it's the sum over the number. 5 over 2, 2.5 is indeed the median of that set. Corollary number three, the median only depends on the middle or the mean of the two middle values for an ascending set. So even if you have one or more variables, you may still be able to determine the median. So we'll see this in a number of examples, but let's say we had a set like so, 1, 2, 3, 4, and X. Now, assuming it was constrained or stipulated in the constraint of the question that they are listed in ascending order, then you could still determine the median is 3 because X has to be greater than 4. If they don't tell you that explicitly, that it's not ascending or increasing order, don't assume it because X could literally be anything. All right, we're moving on from the mean to the median to the mode. The mode is just the most frequently observed number in a set of numbers. You can have multiple modes, you can have no modes. So if we have the following data set, 1, 2, 2, just a collection of values, a collection of numbers, collection of observations. For 4, we're going to have 2 modes because we have 2 2s and 2 4s. All right. As always, feel free to chime in with questions. It's going to be like drinking from a fire hose because we're putting a lot of content and actually going through a lot of questions too today. So we just got really excited about it and had to pack it all in. So please feel free to stop, chime in, ask any clarifying questions as we go. A lot here. All right. The range is going to be simply defined as the max minus the min. We have to be a bit careful sometimes if we have variables in that data set, unless, again, there's a specific constraint defined. But let's look at a very simple example. Data set 1, 2, and 3. What's the range? It's the max minus the min, which is 2. Great. Standard deviation. Standard deviation is a measure of dispersion or spread in a data set. How spread out is the data from the mean? Hold on, what's the mean? The mean is the sum over the number of terms. It's all going to build in itself. So standard deviation is like, how spread out is this stuff from that center, from the arithmetic mean? Corollary 1. The more spread out the terms are from the mean, the larger the standard deviation. Corollary 2, sets of numbers can have the same means and the same standard deviation, but have different values, except if the standard deviation is equal to 0, when all values are the same. So we're going to look at a number of examples of this, but yeah, so we will get to that in just a moment, but let's just stipulate this corollary. But keep in mind, again, for this case of identical values in a data set, even if the mean here is going to be 4, the standard deviation might be 0, because the standard deviation measures, well, how spread out are the values from 4? And they're all 4, so the value of the standard deviation is 0. So we'll look at some examples of this in just a moment. But the GRE loves to ask about transformations of the standard deviation and comparisons of the standard deviation. We'll get to those in just a moment. Okay, attributes of the mean the GRE likes to test, and we'll link this in to those standard deviation corollaries in just a moment. The mean, the arithmetic mean, is skewed by extreme numbers. So we can look at a number of examples for how this plays out. So we have a couple of data sets here. Notice that 1, 2, 3, 4 is identical in all of them. The only difference is the 5 becomes an 100 and the 100 becomes an X. So assuming they are all in ascending order, we'll just focus on the mean versus the median for the moment, for the time being. Assuming they're all in ascending order, and you can assume X is greater than 4 if given to you, then we see, okay, the median in an odd number of values in an ascending set of numbers is just going to be the middle value, which in all cases is 3. But what about the mean? What about the average? What about X bar? So feel free to chime in thoughts in the chat. But what we end up finding is X bar, or the average, is really pulled to the extremes by extremely large or extremely small values. So we don't really know what X is. X could possibly be 4.1, unless we're told it's an integer, or X could be 1,000. So if we actually did the calculation, and you can feel free to run this on your own, you run the sum over the number, we see that the number of terms is constant. It's going to be 5. Using our skills from a whole different lesson in arithmetic, if we increase the numerator, we increase the sum, for instance, by adding the 100 term or adding, say, the 1,000 term, we see that our entire average term is going to go up because the arithmetic mean is equal to the sum over the number. And if the number is constant, but the sum goes up, the average is going to be really pulled towards the left or towards the right, towards really big or really small numbers. All right. So let's take a look at these two data sets. We have -2, 0, 2, 4, 6, -8, 0, 2, 4, 6. So we see we have an odd number of terms, and they're all in ascending order. It's going from negative to neutral, 0, to positive values. So the median, pretty straightforward, just grab that middle number. But what happens to the mean this time? In this case, we have the same exact values, 0, 2, 4, 6, but the only change is the more negative number. So as we go, again, we're going to drill and lots of skill building on actually crunching the numbers and doing the calculations and getting that tangible experience with our own hands. But as we get more experienced and fluent and comfortable with this, what we're going to see is that we don't have to even crunch the numbers. And the GRE loves this kind of low-hanging fruit, where we see the arithmetic mean is equal to sum over number. The number of terms is identical. It's still 5, but the sum is going down because we have a -8 instead of a -2. So the average is going to be smaller. All right. So we have this written out here, the explanations as well. And if you actually want to do the math, you can confirm that. Any questions on any of that? As always, and I'll stop repeating it, but feel free to chime in. Okay, so with that in mind, we're going to revisit standard deviation and some of the corollaries there, because this is deeply related to the relationship and transformations of the mean. So don't worry, don't stress about the fancy notation. It can just be helpful to see it presented in lots of different ways, depending on what works best for you, graphically, verbally, numerically, arithmetically, algebraically. But again, standard deviation is a measure of dispersion, spread, or variation about the mean, about the sum over number, has the same units as the original data. Let's quickly go through this fancy summation notation and see how it's exactly what we said in words before. So this just means, hey, sum up all the terms from the first term to the last, and take each term, subtract it from x bar, from the arithmetic mean, find the difference, square that difference. We only do that because we want to turn the negatives positive. Divide that by the number of terms minus 1, and then take the square root to cancel out the fact that we square rooted it, that we squared it. If that's like, whoa, what the hell just happened? Don't stress about it at all. Just another way of presenting the same idea of how spread out the data is. And we can look again at a simple set of numbers. So we have 1, 2, and 3 as our data set. Now, these are evenly spaced, right? So the difference between each is +1. And so it evenly spaced, and we have an odd number of values, okay? The mean is going to equal the median, is going to equal the middle number, which in this case is 2. You can also crunch the numbers and do the sum over the number and find that indeed the average of 1, 2, and 3, 3 plus 1 is 4, 4 plus 2 is 6 over 3, which equals 2. So lots of different ways to get to Rome, lots of ways to reverse engineer the same idea. So 2 is the mean, 2 is the average, 2 is the x bar. And if we were actually calculating standard deviation by hand, which we don't have to do, but it's a good thing to know that we can do, we just don't have to, because the GRE is a reasoning test, not a math test. what we're literally going to do is take each term, right? So the first term here, and take 1 minus 2, the average, square that. 2 minus 2, square that. 3 minus 2, square that. And do a couple of other things to accommodate for the fact of positives and negatives and so on and so forth. So you can see what we're calculating is basically like, hey, how far apart is each value from that mean, from that average? And then doing a couple of other things just to make sure we're not ignoring the negatives, the zeros, and the positives. So the reason this is relevant is because the GRE likes to ask about what are the effects of transformations or changes to the mean or median or standard deviation. So again, we're going to look at very simple numbers here to just make it super concrete and super tangible. But this is just saying, and it's good to have fluency in both. Hey, we're going to multiply the data set by b, some constant, some value. That could be 2, 3, 1,000, negative 123. And add some term a. That could be negative 7. It could be 5/3, any value. What happens to the mean when we do this is it's multiplied by b and added, and a is added to it. The same goes for the median. But for the standard deviation, we're going to take the absolute value of b and multiply it by that. So if this is like, what is going on? Let's look at simple numbers and break this down for ourselves. So we have a data set, just the numbers 1, 2, and 3. So we have our mean, which equals our median, which equals 2. And we have our standard deviation from this. So let us now transform it. So let's say my b in this case is equal to 2. I'm going to multiply every single set, every single data point in this set by 2. So I turn 1, 2, and 3 to 2, 4, and 6. All right, stop there. What's happened? Well, there's still an evenly spaced set of values. And if we just look at it, we can see that 4 is the mean. So all that happened to it was multiplied by 2 because the average was 2 here and the average is 4 here. Again, you can always reverse engineer it. Gut check, do the sum over the number. In this case, it's going to be 2 plus 4 plus 6. So that's 12 divided by 3, which is indeed 4. So we're just reverse engineering this rule, this idea. So all we did from here to here is we multiplied every single number and we said, hey, here's our little black box. Whatever you give me, multiply that value by 2. You gave me 1, I spit out 2. You give me 2, I spit out 4. You give me 3, I spit out 6. So we transformed this data set by multiplying every value by 2. What happened to the average is that it doubled as well. It also multiplied by 2. And this makes sense if we think about, well, average is equal to sum over number, because again, the number of terms hasn't changed, but the sum has doubled. So what about the standard deviation? The standard deviation, again, is that measure of spread or dispersion or variation around the mean. What we end up finding is that, we'll just compare a simple case again. Let's say we have 2, 3, and 4. Let's say our transformation this time is a is equal to 1. So all this means, my rule is, whatever you're going to put in the black box, whatever you give me, I'm going to add 1 to it, add 1 to it, add 1 to it. Okay, so this simple transformation takes 2, turns it into 3, takes 3, turns it into 4, takes 4, and turns it into 5. So let's look at this case. What happened to the mean? So the mean in this case, the average is equal to 3. Again, you can calculate it. The mean in this case, the average is equal to 4. And again, it turns out the mean, we just added 1 to the mean. How do we know this to always be the case? Sum over number, the number hasn't changed, the sum has increased by 1 for each term. All right. The standard deviation, however, is saying, well, how far apart is each data point from the mean, from the average? Here, it's +1. That's the distance between 2 and 3. Here is +1. That's the difference between 3 and 4. In this case, the distance between each term hasn't changed. So they're as spread out from the mean as they were before. So that just helps us see why when we're modifying a set of values by multiplying it by a certain number or adding a certain number to it, the standard deviation is only going to be multiplied by the absolute value of b. Absolute value, which we review in a whole other lesson, just means, hey, take whatever we're giving you in that black box. Let's say I give you 3 and spit out the positive version. So you put in 3, you get out 3. You put in -5, you spit out -5. So I'll show one more quick example of this as to why we put that b in the absolute value. Again, just to intuit why this actually ends up working. So let's take our data set 1, 2, and 3. And let's say this time our transformation b is equal to -1. So all I'm telling you, hey, here's your rule, here's your black box. Anything you give me, your input multiplied by -1, and that's your output. Okay. So you take 1, you multiply by -1. You take 2, you multiply by -1. You take 3, you multiply by -1. Whoa, okay, this kind of changed order. So let's rewrite it in ascending order. -3, -2, -1. All we did was multiply each term by -1. Now, again, our idea of standard deviation is like how spread out is the data, is the stuff around the middle, around the average. Now, what's the distance between 1 and 2? It's 1. Distance between 2 and 3, also 1. Now, these values are all negative, right? Because we multiplied every single one by -1. But the distance between them, how far apart they are, hasn't changed. It's still 1. Any questions, thoughts about any of these transformations? Again, we're running through a lot, but we're going to quickly apply them and see how they turn into a lot of value on real GRE questions. But feel free to ask any clarifying questions, any thoughts about what we've done thus far. Alrighty. So, a very ambitious lesson plan. We're also going to be diving into an introduction into probability. So, a lot going on, but it's good fun. Probability is a measure of uncertainty. We can calculate the probability of almost any event. An event is the potential outcome of an observation or experiment, right? And these observations that we looked at today in these simple examples are like 1, 2, 3. I walked into a room and I observed and sampled the heights of all 5 people. Okay, so then I just have a data set of all 5 of those heights, those observations. Probability is equal to the number of desired events over the total number of outcomes. Number desired over total number of outcomes. The probability of an event A is always between 0 and 1. So the probability of, say, contracting COVID, or the probability of catching a really debilitating version of COVID once vaccinated, for example, is going to be some value between 0 and 1, or 100% and 0% out of all possible outcomes of, say, health outcomes from a virus. So step 1 is we're going to find the denominator, the total possible number of outcomes. Then we're going to find the numerator, the number of desired events. Oftentimes, the way this presents itself is in games on the GRE. So you might be dealing with a deck of cards, you might be dealing with a bag of marbles, you might be dealing with, alternatively, a real-world event. So we're going to look at some examples of how this plays out. But keep in mind, again, it's just the likelihood of something happening, the number of desired events over the total number of possible outcomes. We find the denominator, and then we find the numerator. Okay, so here's a game. We have 3 dice with faces 1 through 6, so we know what a traditional dice looks like. What is the probability that the sum of the faces is 13? We always want to translate to the simplest possible terms of what the heck they're asking us to do. What they're asking us to do is we're rolling dice 1 and dice 2 and dice 3. When we think about probability and we hear and, we think multiplication. When we're introduced to a probability and we see or, we think addition. So we're rolling dice 1 and dice 2 and dice 3. So what are the total possible outcomes? Remember, step 1, find the denominator. Well, you can either have a physical die in your hand, or recall one side has 1 dot, another side has 2, one has 3, 4, 5, and 6. So the total possible number of outcomes, the denominator in our determination or probability, is going to be 6 times 6 times 6. Those 3 things are happening together. The 3 dice are rolled. And so that's 216. Find the numerator, step 2. What are the possible combinations of faces? So the sum of the faces is 13. Now, there's lots of ways to add numbers to get to 13. Like I could add 10 plus 1. Oops. Let's erase this. 10 plus 1, which would give me 11, plus 2, which would be 13. But hold on, what's the constraint? The constraint is we're rolling a 6-sided dice. So that value goes from 1 to 6. 6 is the maximum possible value. So if we're trying to get up to 13, there's actually not that many ways we can count them. So we can actually manually count them by writing them down on paper. Or otherwise on our iPad. So these are indeed 6 and 6 and 1, 1 and 6 and 6, and 6 and 1 and 6, because we have 3 dice. Now note, and there's a lot here and delved into in great depth in a multitude of lessons and a multitude of drills, but just giving you this kind of really broad 30,000 feet overview of the types of topics and drills we would be working on together, is we have 3 individual dice. Every single one is different. So we often ask ourselves the question, either with replacement or without replacement, or does the order matter? That's a question we ask ourselves when we encounter questions like this on the GRE. And also in real life, hey, what's the likelihood of this happening, of it raining today, of me having to wear a coat outside, whatever it might be. Sometimes we only have a few cases, and we use the same process of finding the denominator and then the numerator to find the probability, the likelihood, the chance of it happening, 3 over 216. All right. We're almost at the questions. Oh, let's see, the question came in. Why would dice faces of 5 and 5 and 3 not count? 3 dice. That is a phenomenal question. The sum of the faces is 13. You are 100% right. In the original configuration, I think it was stipulated away, but thank you so much for that. Who was that? Morgan? You are 100% right. So indeed, you could have 553. Let's see. There's probably actually many other configurations. 535, 355. Let's see if there would be any others. The sum of the faces is 13. Probably some 4s in there too. 4, 4, 5. Wow, there's many other possibilities. So 8 plus 5, 4, 5, 4. 5, 4, 4. And that should cover our bases. 2, 6, 8 plus 5. Actually, there would be even more. Wow. Indeed, the constraint was modified in this question, so I apologize for that. But very, very good catch, Morgan. Thank you for keeping us honest here. So we even have 2, 6, and 5. Yes, we got 5, 4, 4. So we have 2, 6, and 5, 2, 5, and 6. And there'd be a lot of other configurations here too. 6, 5, and 2, 6, 2, and 5, 4, 6, and 3. Yes, there would be many, many, many more. 4, 6, and 3, 9 plus 4, 4, 3, and 6, 3, 4, and 6, 3, 6, 4, 6, 4, 3, 6, 3, 4. Fantastic. So our numerator is much greater than before. And thank you all for catching that. I so appreciate it. Fantastic. So glad that you are watching along. Awesome. We can count these up. 3, 4, 8, 12, 13, 15, 18, and possibly even others. Fantastic. Our apologies. All right. We have a lot packed in here, and I'm looking at the clock. So we might we'll quickly run through this. I think it's just valuable. A lot of content for today. So in our MECE check, what this stands for is mutually exclusive and completely exhaustive. So in our set of observations, or in our particular experiment, in the case we looked at above, we're rolling dice, we're picking marbles out of a bag, or in this case, we're looking at an observation table of lawyers, non-lawyers, and preference for Coca-Cola or for Pepsi. We can present this data in lots of different ways. Now, a MECE check just means when we're drawing our 2x2 tables, our tables of our observations in a data set, we want to make sure that our columns are A and not A, B and not B, are mutually exclusive, they don't cross over, they don't overlap, and completely exhaustive. They cover all the possibilities of what is happening. So what I had up before, those were mutually exclusive, but definitely not completely exhaustive, right? We listed out 18 other possibilities and possibly others when initially we only identified 3. So we can go through a comprehensive MECE check. Hey, if you're a lawyer, does that mean you're not a lawyer? Does that mean you're necessarily not a lawyer? If you prefer Coca-Cola, does that necessarily mean you don't prefer Pepsi as your number one? So we go through and we ask ourselves when we're constructing observation tables and then converting them into probability tables, whether they're mutually exclusive and completely exhaustive. We'll have to skip over and versus or, just in the interest of our time, but to illustrate the mutually exclusive and completely exhaustive nature, of an observation table, then converted to a probability table. So this is just the raw numbers, right? We have 1,000 total people in a study or in a sample, and let's say 300 of them were lawyers who preferred Coca-Cola over Pepsi. Then all we do in the probability table is we take that numerator and divide it by the denominator, right? The total possible set and what is the desired event of, hey, a lawyer who prefers Coca-Cola. So a number of other lessons baked into here, but when we're asked questions like A or B signifying addition, we do indeed have to subtract away the case of A and B to avoid double counting. All right. So we can think about lots of different topics, lots of different data sets. Let's take a look at GRE test takers and performance stats on the GRE, because we tend to look at these when we're considering our grad school applications. Mean is 150, standard deviation is 8 on verbal, mean is 153 on quant, standard deviation is 9.35. Now, the way the GRE scores and the GRE is constructed and designed by the psychometricians at ETS, and the way that many data sets and naturally occurring data sets present themselves are what we often refer to as a bell curve or a normal distribution, centered at the mean, the arithmetic mean, and dispersion created by the standard deviation. So there's lots of different notation for this. This is just a different way of writing S for standard deviation and X bar or average for the mean. But another way of interpreting this, whether it's just the words, hey, the average score is 150 and the standard deviation is 8, is we can construct a histogram or a bar graph, and each single one of these data points is going to be one of us. So that'll be me, and that'll be Morgan, and that'll be Amy, and that'll be Daniella. Each single one of our scores is going to be one little box, right? One little additional data point or value. And maybe we're at the right tail of the distribution, or maybe we're at the left tail of the distribution. So we can present it with a bar graph. Again, a whole set of lessons completely separate on graphical representation in data analysis. And additionally, we'll see an example of this today. We can then make inferences based on distributions that are described as normally distributed. So distributions, just collections of data, the way they're centered or distributed around the mean, can be presented graphically as well, where the probability is on the y-axis and the value, or let's say the score on the quant section, is on the x-axis, right? So again, we have our x bar, our average, in the center of the distribution, and it's symmetrical about the mean, about the average, right? So let's say this is 153 for a quant. And it turns out there's a number of interesting attributes that present themselves both in nature, in the natural world, and in things that are deliberately constructed, like the GRE in standardized tests. So we find that within one standard deviation from the mean, there's a predicted amount of data, of values that are contained within that. So we see here 0.34 and 0.34. So it ends up being 68%. Likewise, between 2 standard deviations from the mean, and likewise between 3 standard deviations from the mean. So the 68, 95, 98, or 99th percentiles we'll see in just a moment, but we also recognize that from when we look at the GRE score chart, and we know, for instance, that a 170, say on verbal, as of a recent tallying chart, constitutes the 99th percentile. So 1% of folks score at that mark, whereas the 170 score on quant is actually the 96th percentile. So 4% of folks score at that mark. A lot to unpack here, a lot of information as well. But again, just whetting our appetite for what we'll look at today in a number of the questions that we can present the same data set. What started out initially as, hey, 1, 2, and 3 can then become a bar chart or a histogram. We can turn that into a pie chart. We can turn that into a graph or a curve as well. All right. So we know quant comparison, A is greater, B is greater, C, they're equal, D, we can't tell. We have a number of general tips and approaches for how we tackle quant comparison, including picking easy numbers, including keeping it weird, testing boundary cases, and we're going to see these examples right here. So, quantity A, the standard deviation of a set of 5 different integers, each of which is between 0 and 10. Quantity B, the standard deviation of a set of 5 different integers, each of which is between 10 and 20. All right. So whether you're a pro and an expert at this and have been running through standard deviation and integers and means before, or whether this is completely fresh, completely new for you in our overview, let's break this down. Let's define it as we go. Quantity A, standard deviation, okay, like how spread out stuff is, regardless of how rigorous we have defined it, of a set of 5 different integers between 0 and 10. Okay, cool. So here it's stipulated that they are indeed different, so that's valuable. And they're integers, so they don't have a decimal after them. Between 0 and 10. I don't know. What are these values? Let's just pick some. 1, 2, 3, 4, 5. Okay, but is that necessarily what it has to be? No. All we're told is they have to be 5 different integers. What else could it be? Well, it could be 1, 2, 3, 4, and 10, right? So these could all be the same between the two, and the only change could be an extremely high value or an extremely low value by comparison, or they could be differently spaced. But these are instructive for picking simple numbers to understand what the possibilities might be. So we don't really know, like, what is the standard deviation? I couldn't tell you, so I don't know what the values are. Okay, it's a good intuition to have. Let's take a look at quantity B. Standard deviation, how spread out stuff is from the mean, of a set of 5 different integers, and there's a wall between these values, so you want to keep them completely separate, each of which is between 10 and 20. Okay, so what are these values? Let's pick easy numbers. Could be 10, 11, 12, 13, 14. Could be 10, 11, 12, 13, 20. Or any other configuration that satisfies the constraints of the problem. Now, the reason this configuration is helpful by just modifying, let's say, one value or testing a couple of simple cases is we can immediately and readily see from a number of different ways, whether we've done the drills, done the number crunching, and can pattern recognize, hey, we don't know, or whether we're actually going through the computation, calculating the difference of each value from the mean, squared all over n-1, taking the square root of that, seems a lot more time inefficient, or whether we're picking simple numbers in easy cases and showing to ourselves, regardless of that intuition or the calculation, that, hey, I don't actually know how spread out these numbers are from each other. So in this particular case, even just picking an extreme can beeline us to D. Lots of different ways to reverse engineer it, lots of different ways to get there. But once we skill build, we do that foundational drilling together, we'll be able to readily unlock it and move on. Daniella.
Awesome. Thanks, Jonathan. And hey, everyone. I'm going to take us through a couple of questions. So this question has 5 answer choices. Select the best one of the answer choices given. We have 2 lists. We have list R and list S. The question asks, the medians of the number the median of the numbers in list R is how much greater than the median of the numbers in list S. So it's asking us for the median. So we see here that the lists are pretty small. They're not tens of numbers, so we're going to calculate the median systematically here. So we'll just rewrite the numbers again in ascending order. So for list R, we have 23, 25, 27, 28, and 30. And for list S, we have, we started out with 15, 17, 19, 20, and 22. And then finding the middle number for each one. And we see here that the medians are 27 and 19 respectively. So the median of the number in list R is how much greater than the median of the numbers of list S. And we can see that it is indeed a 8. It's really important here to always think about also like what is in the test maker's mind. And it's important for us to not go and say, oh, we see the middle, we see 2 lists. We're just going to choose the middle number from each list, which is 15 and 30. So it's important here to ensure that you're really truly calculating the median and not falling into one of the traps that the test makers are setting. Moving forward, another question. We're transitioning back to, instead of a multiple choice like we saw in the previous question, instead quantitative comparison. We're comparing quantity A to quantity B. The arithmetic mean of 100 measurements is 23, and the arithmetic mean of 50 additional measurements is 27. Quantity A says the arithmetic mean of the 150 measurements and quantity B is 25. So what is arithmetic mean? That is just a fancy way or another way of saying average. So, and what is the average that we learned before? The average equals the sum over the number of numbers. So now let's translate what we see here in words into equations. So we have the first average is 23 over the sum, 1, over 100 numbers. And then we see the 50 additional measurements. So the average of the other 50 additional measurements. Sorry, this is a 1 here. Sum 2 over 50. And then we also are having, we're saying we're going to compare these two sums, actually them together, versus the number of the 150 total measurements. So what is this new average, which is in turn quantity A? So sum 3 over 150. In this question, another frame or a way of looking at it is to think about a balancing scale here. So we have this scale, and on one side of the scale, we have 23. And on the other side of the scale, we have 27. And we have 50 measurements over here, and we have 100 measurements over here on the left. In the middle, we have 25. And which way is the scale going to balance? And because we have more measurements on the 23 side of the equation than on the 27 side of the equation, the scale is going to dip here towards the side of the 23. And that's one way of thinking about and guessing or knowing that quantity A is going to be less than quantity B. So another way to approach this problem is to do the calculation. And the way to do the calculation, I'll do it over here, is to say that you would do the calculation of the weighted average, which would be 100 measurements times 23 plus 50 measurements times 27, and you divided that by the 150 total measurements, and that number is going to be less than 25. It's going to be like 24.3. So we know here that actually quantity B is greater, that 25 is greater than the mean of the 150 measurements. So as we can see, there are two different ways of reasoning through this problem, either doing the rote calculation as we see here, or thinking about it more conceptually, about what the test maker perhaps is thinking about trying to get us to understand the concept of weighted average. And with that, I'll pass it back to you, Jonathan, to take us home.
Fantastic. All right, so we've mixed in a lot of concepts in a lot of different ways that they present themselves on the GRE quant in data analysis and looking at mean, median, mode, and looking at standard deviations and looking at linear transformations and probability. And we just scratched the surface of all the possibilities, but we're giving you a sampler for how these questions can present themselves on the GRE. In state X, all vehicle license plates have 2 letters from the 26 letters of the alphabet, followed by 3 one-digit numbers. How many different license plates can state X have if repetition of letters and numbers is allowed? Okay, so we told ourselves we're going to be asking a number of questions when we encounter a probability type question. Are we looking at and or? Are we multiplying or are we adding? Is repetition or is replacement allowed? Sometimes replaced or not replaced in the case of marbles in a bag, or repetition in this case of letters and numbers in a string of values for the license plate. So let's think of what a license plate set of values would look like. And we know we have 2 letters followed by 3 one-digit numbers. Repetition, however, is allowed. So let's think about what these test cases could mean, and then we'll actually draw the numbers. That means if I had A here, I could also have A here. And 3 one-digit numbers, okay, 0 to 9, that means if I had 2 here, I could also have 2 here, but not necessarily so. A possibility, not a necessity. So really, it seems that this could be all 26 letters. Now, are we adding or multiplying? Well, they're all happening together. It's the first and the second and the third and the fourth and the fifth. And we don't have to leave any letter behind, because let's say you can't have another A in a license plate. You can have that other A. So we have 26 possibilities of A, B, C, D, E, and so on all the way to Z. Now, and this is again in highlighting many of the trap possibilities and trap answers, how many one-digit numbers do we have? Well, we can actually write them out and do the calculation ourselves. We can use some consecutive integer shortcuts, which would be the largest minus the smallest plus 1. So 9 minus 0 plus 1 will have 10. Or we just know that we have 10 possibilities for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see where a lot could go awry here if you, for instance, excluded 0 or did not get the total number of one-digit number possibilities. And another way for things to go wrong if you did not continue to account for repetition being allowed. So I can have 0 through 9, I can have 0 through 9, I can have 0 through 9. You're given a calculator on the test. It's not a math test, it's not a math crunching test. You'll find that the answer is E. And you can reverse engineer the wrong answer choices by looking at those traps. Most importantly, how many one-digit numbers do we have, by either just writing them out and reverse engineering them on the fly, or knowing that from our arithmetic work, our arithmetic drilling, or calculating that using the consecutive integers and evenly spaced set rules, which would tell you 9 minus 0 plus 1. Lots of different ways to get to the right answer. All right, our final question of the day And we have a normal distribution, or a beautiful chart given to us. So we had our quantitative comparison questions. We're comparing quantity A and B. The answer choices there were A is greater than B is greater than C, they're equal, D we don't know. And here we have our traditional 5 answer choices, but same approach, same ideas really apply. Okay, so the figure shows a normal distribution with mean M and standard deviation D. We drew this chart out before, including approximate percents of the distribution in each of the 6 regions. Cool, so we don't even have to know that, say, 68% of the values are between plus or minus 1 standard deviation from the mean. Again, if the terminology or the graphs are confusing, boil it down to a simple set of examples, whether that be the distribution of heights in a population or the distribution of GRE scores. For a population of 800,000 subway riders, or let's say 1.6 million GRE test takers, what's the total pool? Here we're dealing with 800,000 subway riders. The numbers of subway trips taken per rider last January are approximately normally distributed with a mean of 56 trips and a standard deviation of 13 trips. Approximately how many of the riders took between 30 and 43 trips last January? Okay, so the mean is 56. So what is the mean plus 1 standard deviation? Well, they're giving us all these values. It's going to be 56 plus 13, so that's going to be 69. What would be 1 standard deviation less of the number of subway trips taken per rider? It would be 56 minus that standard deviation minus that 13, and we get 43. Okay, but before we do anything else, whoa, 43, the question was how many took between 30 and 43 trips? Well, that's nice because what's 43 minus 13? That's 30. So we're given all the values, we're given all the constraints, and we actually look exactly at this region, this set of possible values of the number of subway trips taken per rider last January of the 800,000 subway riders. Okay, so 14% of the values would present themselves or would be between 30 and 43 trips. So that's, again, you can present this in lots of different ways, whatever and more intuitive for you. And we go through all of this in our many arithmetic lessons. But it's going to be of that 800,000. Of that 800,000. Now, are we going to waste our time on calculating this on test day? Absolutely not. We're going to use those shortcuts. So 14% is equal to 10% plus 4%. Okay, 10% of 800K, we're going to move basically 1 0 over. So that's going to give us 80K. And we're going to drill this so we become very intuitive and very comfortable without doing the actual computations. And 4%, that's a little bit tougher. But what's 4% close to? It's close to 5%. 5% would be half of that 10%, right? And just written out, again, we saw 800,000. 10% of that is 80,000. So we're not opening our calculator. We're not actually crunching the numbers, but we're saying, hey, 4% is like kind of ish 5%, which is kind of half of that 10%. So that would be like 40,000-ish, but like less than that, right? Because like 4%, you can actually go even further and say, well, 1%, oh, that's 8,000 of that 80,000, but you really shouldn't because it's a reasoning test and they're not looking for exact computations. In fact, they literally say approximately how many of the riders took between 30 and 43 trips. So particularly if you're short on time, you're like towards the end of a section or what have you, you can already see, hey, if I'm eyeballing this, I got 80,000, 40K, 120. Okay, this is the closest. B, I'm done. Move on. Or flag the question and you want to come back to it. That's fine. You can actually go one step further and find what 4% is, which again would be 5%, which is half of the 10%, minus 1%, which is 10% of the 10%, which would be that 8,000. And that would get you that 32,000 to get you 112,000-ish or so. But again, look at these answers, right? Like there's only one right answer choice and 4 wrong answer choices, all for deliberately flawed and specific reasons. So lots of different ways to get to Rome, but some are more efficient and some can unlock more value. I saw a question in the chat. Will the GRE ever expect you to memorize the standard deviation percentages? Like, I should memorize that +1 standard deviation from the mean encapsulates 34%. So I'll say this as a general rule of thumb. Don't rely and don't stress about memorizing stuff. Our goal and what we found most effective is in that bottom-up, skill-based drill foundational thinking, right? So like, you're not gonna have to make a flashcard and say, hey, I know 68% of the data is between ±1 standard deviation of the mean. Rather, you're gonna keep seeing it over and over and over again to the point where it just becomes as naturally and as imbued in your quantitative vocabulary. But again, it's whatever is most comfortable, most efficient, and easy for you. So if you find it simpler to just straight out memorize the rule, whether that be a formula or the percent of data located between 2 values, that probably isn't the highest impact approach. It's doing the drills, doing the skill building, and then just over time, as you see in this question, so much is given to you. So much is given to you in the values, in the constraints, in what you're solving for, where that really does not end up being the case. It's not a math test, it's a reasoning test using the language, logic, and syntax of high school mathematics. But as you can see, and as you can see in my own work as well, it gets tricky, right? And every part of the GRE test is a reading test. That goes for verbal, that goes for quant, that goes for analytical writing. Every single qualifier and quantifier, every key signal and piece of data or constraint they're looking to see whether your mind will not account for it or make unwarranted assumptions. All right, we've thrown a lot at you today, and we're so grateful for your time and engagement. A couple of valuable next steps is to take a free practice test online, to download the GREMax app on tablet or mobile, sign up for a free 20-minute consult with a GREMax team member. We're more than happy, as always, to stay on after this call to answer any questions, thoughts, reflections about the GRE, about grad school, about GREMax, and the like. And we're also thrilled to share with you our options for tutoring. So working one-on-one, really honing and tailoring the best approach to your goals and your target scores. With that, I'll leave you with some reviews and again, an opportunity to thank you and leave it open for questions. Thank you all so much for engaging and really appreciate it.